Lesson 4, explosions. Actually, we're going to start off with some terminology. There are two main types of collisions. Objects bounce off of each other after the collision, curling being a good example. Billiard balls, pool. Baseball and bat, tennis racket and tennis ball, golf club and golf ball. Some car crashes, there are some where they don't bounce off of each other, but some car crashes. Hockey body checks, another good example. We have a fancy word for that. We call these collisions elastic collisions. And the way I remember that is I think elastic band, rubber bounce apart. Okay? An elastic collision is one where the objects bounce off of each other. Throwing a ball against a wall, having it come back to you. Okay? There's a second type of collision. It's where objects stick together after the collision. Football player tackling and holding on to the ball carrier. A dart hitting a dartboard, arrow hitting a target, sticking in. If a bullet sticks into the target, some bullets will go through. That would not be this example. That'd be the first example. Some car crashes stick together. We have a fancy name for that. We call it inelastic. The opposite of elastic. Now, there's a bit of a problem here, Courtney. If I talk about an elastic collision, it's very hard for you to tell which one I just said. Oh, got a latecomer coming in. There's a problem. If I say an elastic very quickly, it's tough to tell whether I said an elastic collision or inelastic. I'll try and emphasize it. You'll often hear me say two cars collide inelastically. Or another late person, 2 in a row here. Boy, that totally derailed my train of thought. 2 kids coming in late. I was saying, I'll emphasize it. Or you'll hear me say there was an elastic collision. I'll try and pause and make it obvious. We're stuck with it. Those are the terminologies. Okay. I have here video collision examples. I'm going to show you that at the end, actually. Instead, let's look at an explosion. A good example of an explosion is a rifle shot. A rifle shot. Rifle bullet leaves the muzzle with the velocity of that. If the rifle is held very loosely, with what velocity will it recoil? It wants me to find a velocity. There are 2 objects, bullet and rifle. This is a job for conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. Before I pull the trigger, before the explosion, what's moving? The rifle, the bullet, both, or neither? Come on, people. Before I pull the trigger, what's moving? The rifle, the bullet, both, or neither? Neither. What's my initial momentum then? What's my final momentum then? Also 0, but I think it's going to be 2 objects traveling in opposite directions. So I'm not going to put a 0 on the other side. In fact, I'm going to say, after I pull the trigger, after the explosion, what's moving? The rifle, the bullet, both, or neither? Both. Both. You know how I know both? What am I asking you to find, Prith? Right? Of the rifle. Both. Stuck together or separate? Unless something's gone horribly wrong, separate. Right? How about momentum of rifle final and momentum of bullet final? And again, as you get good in your homework, you can start to take shortcuts like I did earlier in class, going over the homework with you. I just never would. On a test, I'm meticulous. On a quiz, I'm meticulous. I don't want to make mistakes. Hey, momentum P is what times what? Lydia? Okay, so I dropped the 0 down. Rifle is going to be mass of the rifle, velocity of the rifle, plus mass of the bullet, velocity of the bullet. I've even been lazy. I've dropped the finals because there's only one velocity anyway. There's not an initial velocity, so I'm in no danger of getting them mixed up. Prith, what did you say this question was asking me to find? Which is what in here? Yep. Okay, how would I get that by itself? And it's going to be 0 minus the mass of the bullet, v bullet, which is just negative mass of the bullet, v bullet. Mass of the rifle, v rifle. Keep going, Prith. How would I get the v by itself? Can I do that right now, if that's okay? Cohen, what's the significance of this negative? If the bullet is going north, the rifle recoiled. If the bullet is going right, the rifle recoiled. Or you know what, let's be generic. Bullets ideally go forwards, rifles recoil. There you go, okay? So I'm not gonna add a direction, I'll just put a negative in front of my final velocity, and that's my way of telling the marker in the opposite direction on the bullet. Oh, we can plug and chug now. The recoil velocity of the bullet, of the rifle is gonna be negative mass of the bullet, 0.06, that's a pretty heavy bullet. Ooh, 60 grams, that's got some heft. You know what? In fact, I think I looked these up. I think I took one of the sniper rifles from one of the Call of Duty video games and used its speed and bullet mass. Those of you that have played those games. I think this is one of the big sniper, and if you have played those games, I know at least one of them, there is some pretty impressive recoil on that thing. Although the physics in that game is still lacking sometimes. Although I haven't played the last couple of versions, maybe they've gotten better. V-bullet, 600? Yeah, this is a sniper rifle because the speed of sound is 330 meters per second. This is almost double the speed of sound. This thing is hauling. This would do some damage. Divided by mass of the rifle, 3. Negative. I think I can do this in my head. The 6 and the 3 can't, it's 200. 12. Double check me. I got the negative already. Yeah, 12 meters per second. You guys might recall way back just after Christmas, I showed you a forces come in pairs video of these guys shooting elephant guns and seeing the rifles recoil. This is the same physics, but you can think of it not just in terms of forces come in pairs, but you can analyze it in terms of momentum. You can actually crunch numbers. It's a natural consequence of Newton's third law. Example 2. Spencer is sitting on a canoe, floating on the water next to the dock. I shall be Spencer. The dock is to my left, your right. Spencer decides to stand up and step out of the canoe onto the dock. Why does he get wet? He will. I used to teach canoeing at a summer camp, and I used to see this all the time. It was great fun. Maybe I should replace the word Spencer with Sheldon, and then he wouldn't be foolish looking at his phone. Yeah, I caught that. Sheldon, my friend, I am going to pick on you. Right now, what's my momentum? What's the momentum of me and the canoe that I'm imaginarily standing in? 0. What must our final momentum be then? 0. So if I have momentum this way, what must the canoe do? It must have momentum that way. Who has a bigger mass, me or the canoe? I'm flattered you think that, but canoes don't weigh very much. Canoes weigh 50 pounds, maybe 100 pounds at the most, but they're ideally designed that you can portage them so you wouldn't have them very heavy. I'm going to ask you again, who has a bigger mass, me or the canoe? Who's going to have a bigger velocity then? Canoe. As I do this, maybe at 1 meter per second, the canoe's going to move that way at 2 meters per second. It's not going to work very well. Or if you have, probably as kids, or maybe even now, if you've ever tried, if you're in a swimming pool or in a lake, balancing on a floating toy, inner tube, little boat, if you die right now, you and the boat have 0 momentum. If you dive forwards, which way must the inner tube move? And because the inner tube has such a little mass, it often shoots out from underneath your feet because it has to have a really big velocity for the equation to work. And that's why that, you belly flop or whatever. It's still fun, but that's the physics of that. Okay? So, how about this? Oh, you know what? I don't need to write this in English. Let's write this with symbols. Momentum initial is 0. Better yet, let's put a little sum of in front. The total momentum is 0. If Spencer moves right, Canoe moves which way? Left. And then you can put in brackets faster since smaller m. Now Matt's thinking, well, okay, then how do you get out of the canoe? There's 2 ways. Method number 1, especially if there's 2 of you, one person grabs the dock and continues to pull the dock towards them and applies a continuous force. The first person gets out, then that person, once they're on the dock, holds the canoe in tight. By yourself, you turn, my momentum is still 0, you sit your butt down on the dock, the canoe will move forward a tiny bit, but even if it does, because you've got one of the largest parts of your body heading for you're going to land on the dock, you're going to end up sitting on the dock, you hook it with your feet, pull the canoe back in, and you can safely get out. Or, with one hand, you can hold on while you're getting out, but canoes are tippy, that's trickier than you think. I told you that on water, the person in the canoe has 0 momentum. Sheldon looked at me skeptically. So what do I mean by an explosion? To me, an explosion is when your initial momentum is 0. Keep putting it away and leave it away. Thank you. Another good example is if you've ever done this while ice skating, face each other and give each other a big push on a frozen ice or frozen pond. A boy and a girl are standing in the middle of a frozen pond. The boy gives the girl a push, as shown, and she moves off with a speed of 2.4 meters per second. With what velocity does the boy move off? Okay. This is an explosion. This is a job for conservation of momentum. There's 2 objects. The sum of all the momentum before equals the sum of all the momentum after. What's my initial momentum of both objects? 0. Let's take a little bit of a shortcut in our notes. Normally, I would now write momentum of the girl, momentum of the boy. How about I'm going to go straight to mass girl v girl plus mass boy v boy. Is that okay, Cohen? What does this question want me to find, Cohen, my friend? Read part A out loud. Yep. Oh, this one here? This one, right? How would I get that by itself? I think the first thing I'm going to do is move this over. And it'll just become negative because it's a 0 on the other side. Yeah? In other words, the first thing I'm going to do, I'm going to have negative mass girl v girl equals mass boy v boy. You okay with that, my friend? Yeah. How would I get the v boy by itself? What will I do with the mass of the boy? How will I get this by, what's this doing? Adding, subtracting, multiplying, or dividing onto that? How will I move it over then? You don't say. Can I do that on this line? Yeah. By the way, looking at this, which person is lighter, the girl or the boy? Who will move off faster, the girl or the boy? Because he's lighter. Okay. plug and chug. The final velocity of the boy is going to be the opposite direction of negative 60 times 2.4 divided by 45. Negative. Can I do this in my head? 60 divided by 2.5. If I divide, it's 4 over 3. So 2.4 divided by, it's 3.2 negative. Double check me. Yeah? Meters per second. Or if you said, because there's a picture, we can actually add a direction. We can say, hey, you know what? Really, what direction is the boy moving? 3.2 meters per second. Direction? Right, or east, or, yeah, I'll go right. You okay with that, Alex? Alex, what's part B asking me to find? It does. Folks, what's another word for impulse? Change of momentum. And it wants me to find the impulse of the boy, one object. So I'm not going to use conservation of momentum. There was two ways to find impulse. One way was the one that had the force and the time. The other way was when you had the final and initial velocity. Court, which one do you think I'm going to use here? No. So there's two ways. Don't write this down, just watch. I can find impulse by going force times time, or I can find impulse by going that. Which one am I going to use here? Yeah, because I don't see a force and a time anywhere. In fact, I think later on they ask me to find a force. So, okay, I think this will work, Mr. Duick. You can write that down. Alex, what was the mass of the boy? What was the mass of the boy?
This one?
Yeah, you.
Oh, man. I don't know.
Look at the picture.
I'm looking at the picture.
Yeah,
Oh, 45 kilograms.
this is meant to be obvious. I'm giving you low balls, my friend. You should be able to handle these okay. What was the final velocity of the boy?
Oh, dang, what are we talking, 3.2?
Look at the picture. What was the initial velocity of the boy? Yeah, oh yeah, I'm going through a question with you.
Initial velocity,
Look at the picture.
look at the picture. Or wait, the boy?
Well, really, what's the initial velocity of both of them?
2.0? Oh, 0.
So I can do that, yes? In terms of a direction, I think the boy's impulse will be to the right. 45 times 3.2, okay, I might need a calculator for that one. Let's go see. 45 times 3.2, 144? What are the units for impulse? Well, it's mass times velocity, and I'll even add a direction. Good yawn, Sarah? Excellent. I can do part C with no work, not writing anything down but the answer. What's the impulse of the girl? 144 kilogram meters per second. Which way? Left. That is the law of conservation of momentum. Whatever one person gains, the other person has to lose. Does part D ask you to find the force? Okay. Well, I just found the impulse. You know what would be cool? If there was an equation that had force and impulse in it. Courtney looks at me because this time she's paying attention and she says, yes, there is, Mr. Dewick, this one. And I say, oh, you are ever so clever. How would I get the force by itself? Divide by the time. So the impulse was 144. The time is 0.25. 144 divided by 0.2. Oh, I can do this in my head. Dividing by 0.25 is the same as timesing by 4. It's going to be 400. Well, it's going to be 288 times 2. It's going to be 400, 576. No? Yes? You didn't give me any body language. I was looking at Andy. He never twitched. I was like, okay. 576 newtons. I can even add a direction. Which way did the boy push the girl? Left. They didn't really ask for a direction, but okay. So, what's an explosion? Your initial momentum is 0. Your final momentum is also 0, but I usually break it up into 2 separate parts, one positive, one negative. This is also an explosion, but this time it's a little bit different. So it says this: a space capsule consists of a 2,500 kilogram main capsule and a 1,500 kilogram probe. The space vehicle is traveling at 120 meters per second when an explosion occurs, boom, between the space capsule and the probe. After the explosion, the probe moves forward at 280 meters per second. What's the new speed of the main capsule? Hey, is there an explosion? Yes. Are there 2 objects? This is a job for conservation of momentum. And because this one's a bit weird, I'll go a bit more careful. I'll start out by writing the sum of all the momentum before equals the sum of all the momentum after. Ryan, my friend, before the explosion, what's moving? The capsule, the probe, both, or neither? Look at the picture. Stuck together or separate? So, momentum of both initial. Boom! They explode. After the explosion, Ryan, what's moving? The capsule, the probe, both, or neither? Stuck together or separate? How about C for capsule? P for probe? Okay. By the way, let's make some predictions. Look at the probe. What's its final speed? What was its initial speed? Did the probe speed up or slow down? What do you think happened to the capsule then? Slowed down, because the capsule lost impulse, lost momentum. The probe gained the same amount of momentum. See now it's all put together? Okay, let's keep going. Momentum is what times what mass? So this is going to be mass both VI equals mass capsule V capsule, mass probe V probe, and I'll put vectors on all my velocities to remind myself to be careful looking for a change in direction. In fact, if this was a really powerful explosion, Jess, this capsule could actually have been forced backwards. I'm looking at the arrow, I think it's moving forwards, but if I get a negative answer, then I would say, oh, they were moving along, boom, this thing went shooting backwards, and the probe really took off. This is actually one of the reasons we use 3-stage rockets, why we use booster rockets. You lose a mass, and you gain more velocity. Oh, yeah. You've seen videos of rockets, like the old space launch, the moon launches, where all of a sudden you see one of the engines drop off. That's why. Okay. Rye, what are we trying to find? That baby right there, right? How would I get that by itself? I think first I'll deal with that there. How? And then what will I do with this mass right there? Could we do that one step? Okay, so the M both, so I think what you're saying, and you're right, the M both V initial drops down like a domino. Well, it stays where it is. I subtract that, and you said divide by the mass of the capsule. I totally agree with you, right? Yep. Oh, let's crunch it. Mass of both. Ryan, can you add 2,500 and 1,500 in your head? Did you actually add it, or did you clue in that I actually, at the beginning of the question, told you the mass? I think I did at the beginning. Yeah, I did. Okay. 4,000. Initial velocity, Rye? Yep. Minus mass probe. Velocity probe. Now, I'll ask, this isn't meant to confuse you, but this is to remind you to check. Should that 280 be positive or negative? I think we've decided that right is positive, so it is positive, but always get in the habit of checking and asking, because vectors make a difference here, okay? Divided by mass capsule. And I'm expecting an answer less than 120, because I think the capsule slowed down. Brackets, Mr. Duick. 4,000 times 120 minus 1,500 times 280 divided by 2,500. 24? I could add a direction, although the question only asked for the speed, not the velocity, and speed is a scalar. So 24. John, what's part B want me to find? Oh, that's going to be the change in momentum, which is going to be mv final minus mv initial. I went with that because it looks like there's lots of velocities kicking around, and I don't see a force and a time anywhere. All right. Hey, John, what's the mass of the probe? What's the final velocity of the probe? Minus mass of the probe, 1,500. What's the initial velocity of the probe?
120.
Yep. By the way, the probe gained momentum. It gained impulse. I think we're going to get a positive answer. $240,000? Yeah. 240,000 Newton seconds or kilogram meters per second. Why can I do part C showing no work in my head without even thinking? What's the answer to part C? Yep. It's, you know what? I'll even, negative 200. The capsule lost that much, the probe had to gain that much. That's the law of conservation of momentum. We've been doing it mathematically, the sum, but if you happen to know the numbers, you can kind of just reason your way to it as well. A couple of conceptual questions. Mountain climbers use nylon safety ropes due to their tendency to stretch considerably under stress. Using physics, tell me why. What does the stretching change? Which variable does the stretching change? Yeah, time. Because you know what? First of all, for any mountain climber, I think it's safe to assume if they fall, their initial velocity is 0. I've never seen a mountain climber, I'm going to throw myself down off the cliff. Okay, so VI is 0. VF is however long they fall for. But here's my point. We have an impulse, a changing momentum, because the final and initial velocities are different. And you're telling me tiny force, big time, and you'll be okay. In fact, what's the ultimate example? What thrill-seeking sport do people do that takes this to the nth degree? Bungee jump. That's the whole physics behind bungee jumping. You're stuck with a change in impulse. You're falling a fatal distance. But if we can lengthen time, I've told you, it's not the force that kills you, it's not the time that kills you, it's really the acceleration, but the F has the mass and acceleration in it. Okay. Why does conservation of momentum explain why it's so difficult for firefighters to hold hoses that are ejecting large amounts of water at high speed? Before you turn the hose on, what's the momentum of the firefighter and the hose? What must the momentum be afterwards then? 0. So we have large MV forwards, water, and especially the more you open up the hose, the more mass times velocity you have going forwards. Both the velocity of the water increases and there's more water molecules. Means large MV backwards. And so the firefighters have to lean into it. In fact, they have to apply, listen close, a force times a time. Which is also why you get tired, because you're applying a force for a long time. Anybody here use a fire hose? Anybody here in the fire academy? Yeah. It's no, just a fire hose casually, like you have one at home, or your dad's a fireman. Okay. So you got to use one at full blast, or did they only just crack it open a little bit? It's by the way, you've even, if you watch in the 1960s in the civil rights movement, and even nowadays, they use water cannons to disperse crowds. It's not like, oh, we're running through the sprinklers. If you look at those water cannons, especially if you look at the black and white footage from the 1960s civil rights arguments in the U.S., people are getting knocked off their feet and thrown. Well, that's a momentum issue. It's a collision. It's a conservation of momentum. The diagram below shows 2 pop cans of unequal mass. In fact, one has a mass of m, the other has a mass of 2m. An explosive charge is detonated between them. Boom! And they fly apart. What can you tell me about their velocities after the collision? Yeah.
The one on the left has to be double the one on the right.
The lighter can goes at twice the speed. Yeah. And the reason is, it says, using principles of physics, explain your answer. What's your initial momentum here before the explosion? 0. What's your final momentum? 0. You know what? They have the same impulse. Both of them have, so I'm going to say this. How about I call this can 1 and can 2? The impulse of can 1 equals negative the impulse of can 2. Haley, you okay with that? Impulse is going to be, oh, put a vector there too. Impulse is going to be can 1 V1 final minus, oh, what was V initial for can 1? Before the explosion, how fast is can number 1 moving? So normally I'd write minus initial 0 equals negative can 2 V2 final. That's what you said. So are you with me so far? Here's a proof. Let's see if we can end up with what both of you said. What's the mass of can 1? M. Here's V1. Negative, opposite direction. What's the mass of can 2? 2M. Here's V2. Is there an M on the left-hand side? Is there an M on the right-hand side? I'm going to divide both sides by M. And if I do that, Matt, they're actually just going to end up canceling. And do you see what I have left? What did you, Trevor, you gave me the, was it Trevor that gave me the answer? What did you say? Or was it you that gave me the answer? You did. What did you say? The lighter can goes, ready? The lighter can goes twice as fast as the heavier can. See how I'm left with that left behind? There's an algebraic proof. I'm not going to ask you something like that on your test, Ryan. Physics 12 right there. We'll do a lot more. Look, instead of using numbers, let's prove it once algebraically. We got a rule and use it. What's your homework? Every question, but can you change, if you look, number 1, part 2, after the blank, that should be the word speed. Because I said the recoil speed of the gun is, I have to compare speed to speed, not speed to momentum. Your homework is every question. Okay. I was going to show you some videos of collisions today. We'll start off tomorrow with that. So remind me, make sure I don't forget. You got the rest of class. Where you go. Oh, by the way, before I turn you completely loose, these are meant to be collision diagrams. I yoinked these from the internet. Just hang on. So this is supposed to be mass 1 is moving at 2, is 2 kilograms, moving at 5.2. Mass 2, since there's no arrow on it, how fast is it traveling? 0. And then this is supposed to be, they stick together, as opposed to this one down here where I have 2 masses moving and they don't stick. Oh, I can use the magic word. Elastic, inelastic collisions. So I just wanted to give you a bunch of practice with every possible combination. Head-on collisions, bouncing apart, elastic, inelastic. Then at the very end, there's 2 really, you know what? I'm going to say, no, we'll go every question. 12 and 13 are nasty. I'm not going to give you one this tough. Okay, now I'll turn you loose.